This is a discussion that's kind of an entry level for object-oriented programming. We like to do some beginner level talks at YAPC, and so if object-oriented programming is all that you do, then there are other great talks to see as well. But if you want to stay and enjoy some of this, then please do. My name is Dave Oswald, and I enjoy Perl. That's it was back in the mid-90s. I had been programming in C and in C++, and then I picked up a Perl book, and suddenly everything changed for me and how I looked at programming. And so I'm a Perl enthusiast. I also participated in community advocacy. In the past, I was an organizer in previous years for this conference and for Open West, and I organized the Salt Lake Perl Mongers. I'm a software engineer at Endurance International Group, so I want to thank Endurance for letting me be here today. We're the company that owns Bluehost, and there's a few familiar faces in the room here, so thanks for coming out and supporting us as well. So our goal today is to learn some simple thought processes that are useful to programmers and see how they can be applied to our work. And in specific, relating to object-oriented programming. So the first thing I wanted to talk about is encapsulation. Anybody familiar with this concept? Okay, so encapsulation, to completely enclose. But before we talk about encapsulation, I'd like to talk about substitution. I had a note here on how to pronounce these characters. Let's say phi and phi. So where phi and phi represent formulas, is that what those are? I don't know what I can't remember what they are. Phi and phi, yeah, represent formulas. Phi is a substitution instance of phi if and only if phi may be obtained from phi by substituting formulas for symbols in phi, replacing each occurrence of the same symbol by an occurrence of a formula. So that's a pretty complex explanation, and it comes from Wikipedia. And if that's the way that CS 101 is taught, then we're all in trouble. So let's talk a little bit more in depth about what substitution really is. And this is the more detailed explanation. It's to put something in place of another thing. And so let's consider the example of a factorial. And so we tend to use, over here, I'm going to use my laser, we tend to use n with an exclamation point to represent factorial, right? But what is factorial really? Well, it's this algorithm right here. And that's a mathematical representation of the algorithm. It's not a code representation. So, or we can look at the representation a different way, where we're going to take n and multiply it by n minus 1 and multiply it by n minus 2 and so forth until we get to 1. And so, but because it's really hard to reason about formulas that have all of this in them, we tend to use just this. And so we will tend to say 2 factorial plus 3 factorial instead of saying 2 times 2 minus 1 plus 3 times 3 minus 1 times 3 minus 2, because that's just too laborious, right? And too hard to reason about. And if we did that for every type of formula, then we'd end up with a big mess as we're trying to solve problems. And this is just in the realm of mathematics. So we like to represent things in simple ways. We take the complex concepts and represent them in more simple ways. So we can say that another way to look at it is that n factorial is n times the factorial of n minus 1. And so then now we're getting recursive. So let's move away from factorial for a minute and talk about something else that's really important in life, and that's goats. And so goats are made up of a lot of different parts, and farmers don't tend to have to think about all of the parts all of the time. And if they did, then they'd have trouble dealing with their flock of goats, because goats tend to be they tend to be curious, and they tend to be trouble seekers, and they end up in crazy situations, and they like to eat your clothing and all that sort of thing. And so it's really hard to keep track of all of the things about a goat when you're dealing with the goat himself. Just the goat's personality and who the goat is. And so this is where we get back to the idea of, and so we substitute all of these difficult things about a goat just in the term goat. And this is our substitution. And when I say goat, then you're all thinking, well, the thing at the petting zoo that eats my clothes and that has little horns and all of that sort of thing. So we use substitution to kind of gloss over all of the details. So this takes us back to encapsulation, which is to completely enclose. And so let's encapsulate our factorial. This is Scheme because I happen to like how factorials are represented in Scheme, but we're at a Perl conference. So, and I think it was Larry that said that Scheme has all of the, all of the visual appeal of fingernail clippings or something like that. So, yeah, oatmeal with fingernail clippings in it. So I guess I should have had a oatmeal slide up there. So we'll look at the Perl one, which is much better.
Said that at a talk, and Joseph McCarthy was in the audience, and he didn't know it. Joseph McCarthy was not close.
Oh, really? That's great. So we're going to look at the factorial here, and we've done a recursive version of the factorial, which is to say that that we are going to take x and multiply it by x minus 1. And then in the end, on the right over here, we just, when we want to use our factorial, we just say factorial 5, for example, and it's going to print out 120. So this is a really easy way of encapsulating behavior. We encapsulate behavior in subroutines, essentially, in Perl. There are other things that we can encapsulate. We might encapsulate pi as just a variable. We might encapsulate primary colors, red, yellow, blue, giving them a label of primary colors. So in Perl, that might look like my pi equals 3.141592654, and we might say my primary colors as an array equals, quote word, red, yellow, and blue. So these are just ways that we use substitution to encapsulate ideas and concepts so we don't have to keep thinking about them. Let's look at a little bit more complex encapsulation. So this is a flight recorder. And a flight recorder really does one thing. It keeps a history of everything that's going on, right? It keeps a history of all the things. And so I imagine that inside it's fairly complex. And we hope that we almost never have to deal with that complexity. We just hope that it's going to collect all the things and keep a record of them, keep a history of them. And so what this flight recorder is doing is actually it's encapsulating or completely enclosing both state, which is data, information, history, and encapsulating functionality or behavior. And the behavior that it's encapsulating is it's going to be recording everything that's going on during the flight that's worth recording. So we're going to completely encapsulate and enclose state and behavior. And why would we do this? Any thoughts? I'm willing to. This isn't one of those talks where there's no interaction allowed. Well, one reason that we would want to completely encapsulate state and behavior is that when you're coming in for a landing on the approach, just about the last thing that you want your pilot to be worried about is what's going on inside that box. What's going on inside the encapsulated device. Because if they have to spend too much time thinking about the aircraft interface board and the memory interface cable and the high temperature insulation, there's a high amount of cognitive load associated with all of that. And they're a little bit busy at the moment trying to land a plane. I mean, they've got some instruments. Nowadays, it's maybe not as busy as it used to be. I don't know. I don't fly planes. So we don't really want them thinking about what's going on inside the plane, or else they'll end up going off the runway. And that can happen. And when that happens, then you break encapsulation. So let's get back to goats for just a minute. What's that? Yeah, here we are back to goats, because why not? So goats have all these different parts, and this is maybe only a butcher's concept of a goat, and a farmer's concept of a goat might be more along the lines of that it's small livestock and has horns and horizontal pupils and eats almost anything and is curious, and that it's a trouble seeker. And then there are, the internet's concepts of goats, and this is really kind of what we want to deal with, is just the overall concept of a goat. We want to get rid of all of the detail and think of just the nice goat out there having a great time and being essentially a mischievous goat. So this is where abstraction comes in, and abstraction is the process of removing physical, spatial, or temporal details or attributes in the study of objects or systems in order to more closely attend to other details of interest. It is also very similar in nature to the process of generalization. So this is from Wikipedia again. So this means now we have another problem. We need to discuss generalization. What is generalization? Broadening of application to encompass a larger domain of objects of the same or different type. Again, from Wikipedia. None of this makes a whole lot of sense when you just look at the words. So let's talk about generalization. Anybody familiar with what this is? Dremel Tool, right? This is a generalized tool, sort of, for some types of tasks. Like I've got a Dremel tool, and it always seems like it's a great thing to have. Like I really need to have that Dremel tool, and yet I can't really ever find any applications where I actually need to use it. So it mostly just sits. But anyway, it's a very generalized tool. But what does it do? What does a Dremel tool do? It spins a bit really fast, and it has a hand grip. That's what it does. It does just those two things. It spins a bit really fast, and it has a hand grip. But it can have its application broadened by specializing it with its range of tips, right? So this is a generalized tool, and this is not a very generalized tool here. This one will do one thing and one thing only, and that's to put holes in, I guess, wood in the 1800s. So Dremel tool is a generalized tool. But we're going to talk more about the Dremel tool in a little while, but first let's talk about the lowly hash. We're all familiar with hashes. We use them every day in Perl, and they're part of what made Perl great 30 years ago, and they're part of what are making other languages great nowadays as well. So in Perl, we would say my hash equals, and then foo 42 and bar 84, and then we can say hash foo and get our 42 back. So it's an index thing. And on the front side, we as programmers are glad to just only deal with that. That's very simple. We can think about it. We're indexing into a hash by selecting its element foo. And we can use hashes for all kinds of useful things. But under the hood, hashes are actually kind of complicated. The way a hash has to work is that you start with your keys, and the keys go through a hashing algorithm that decide which bucket they're going to go in. And then anytime you have a bucket collision, then you have a linked list. And that's why you don't want your buckets to get too huge, because eventually you end up in a little bit of a linear search here through your linked list. It turns out that because we don't have to think about it, we can, in more CS terms, we can say that hash lookups occur in constant time, in amortized constant time. And hash inserts happen in amortized constant time, and we're able to generalize about the concept of a hash, even though inside they're really complex. Perl's hash consists of a whole bunch of different little pieces and little parts to make this whole thing work so that we can have something simple like this on the front. So a hash encapsulates a whole bunch of craziness and a whole bunch of stuff that we never want to think about unless you like dealing with Perl guts. Which is sometimes fun, but usually not when you're trying to optimize for getting work done. So the hash API really is doing very few things. If you think of what the hash API is, just only one layer under the hood instead of all the way in the guts. A hash API has a constructor, and it has a store and a fetch and a first key and a next key, which is used for things like this and keys. And it has an exists and a delete and a clear and a scalar. And scalar is like the most useless part, although I guess it's become more useful in recent versions of Perl. But each of these things, each of these concepts are represented in our space as Perl developers as, for example, the constructor, my hash equals whatever. A store would be to insert a key. A fetch would be to find the value in a key. Each makes use of first and next key. Exists passes straight through as a function. Or as an operator into Perl. Delete is an operator in Perl. Clear is essentially assigning an empty list, and scalar is, again, kind of that useless thing where we just find out if it has keys or not, essentially. That's about all it's useful. But this fairly simple interface that we use every day of our jobs is really under the hood doing all this crazy stuff that we don't have to think about. And this is a perfect example of a nice, useful abstraction that is a result of encapsulating a bunch of both data and behavior. So a Perl hash is an object abstraction encapsulating data and behavior and removing unnecessary detail from the interface, which allows us to concentrate on solving higher level problems like finding unique things easily, right? So an abstraction is an emphasis on an idea, qualities and properties rather than the particulars. So it's a suppression of detail. So in the case of a goat, it's an emphasis on the idea or the qualities or the properties rather than the particulars. So there is famous quote that I really like that says, all problems in computer science can be solved by another layer of indirection or abstraction. And that's kind of what we're seeing. I'm going to go back a little right here, is we're seeing a problem in computer science, finding unique things being solved by a couple layers of abstraction or indirection here. We have a scene hash, and we have grep, and now we've got an anonymous subroutine. These are all layers of indirection or layers of abstraction. Any questions? Everybody with me here? So, now let's talk about object-oriented programming a little bit here. And the world is seen by an object-oriented programmer, all these different little things. When you start thinking of the world in terms of objects, when you start learning about object-oriented programming, you start seeing objects in everything, and you start, it's your new hammer, just like when you first learn regular expressions, that becomes your new hammer. But the concepts that are basic to object-oriented programming are classes, and a class is just a specification of attributes which can be considered state, and methods which can be considered behavior. So a class is just a name that stands for a specification of state and behaviors. And then objects are just instances of classes. So a goat might be a class, whereas I don't have any goats, but my neighbor's goat named Chops might actually be an instance of a goat, right? Okay, so classes are specifications of data state, objects are instances, attributes are the characteristics of an object, and methods are things that an object can do. So I've promised not to use animals in my talk, and now I'm going to use animals because I was talking with Randall the other night at the arrivals dinner and said, I'm not going to use animals. And he said, why not? They actually work pretty good for this. And he's right, and so I'm going to use animals. I went back and changed a few slides. And so we're going to talk about the concept of an animal as a living organism. It's multicellular. It feeds on organic matter. It has specialized sense organs. It has a nervous system, and it responds to stimuli. That's kind of the basic, I guess, definition of an animal. There's probably additional things we can layer in there. So there are types of animals. There's mammals and reptiles and birds and fish. And then in the mammals, we have dogs, and dogs have all of the characteristics of mammals. So a dog is a mammal, and a mammal is an animal. Good with all this? So this takes us to inheritance. And inheritance really can be expressed like here's another example of inheritance. A vehicle can be a wheeled vehicle or a sailboat, and a wheeled vehicle can be a bike or it can be a car, and a car can be a sedan or a coupe. So we can talk about Sandy, which used to be my dog. So Sandy is a mammal, and she's a dog, and so a dog is and then Sandy, my dog, is an instance of dogs in general, and my dog has a name, and her name is Sandy, and she has a breed. She's a golden retriever, and she has a personality, and she's a female, and she responds to a set of commands occasionally, and she has a date of birth, and walks and eats and drinks and poops and sees and sleeps and plays and barks and sniffs, all the things that dogs do, because she's an instance of a dog. And so how does Sandy relate to object-oriented programming? Well, a dog is a type of thing, and so a dog is a class, and an instance of a dog is an object in that class. And a dog has attributes. It has state. It can be awake. It can be asleep, happy, sad, hungry, mischievous. And a dog has behaviors. They can wag their tail when they're happy, and they can eat and drink and so on. So if we look at Sandy as an object or as an instance of dog class, then her attributes are specific to her instance of dogdom, and her actions and methods that act upon her or are done by her. So in inheritance, the class dog inherits many of its traits from mammals, and mammals inherit many of their traits from animals. And so as Sandy relates to all of this, we might consider an animal as a base class, or technically an abstract base class, because you can't just be an animal and not anything else, not some type of animal. And a mammal might be an abstract class that inherits from an animal. And when I say abstract, I mean you can't really instantiate just a mammal. It has to be a type of mammal. And a dog is a class that inherits from mammal, and Sandy is an object of instantiation of the dog class. So Why do we use classes and objects? Any thoughts? We've been talking about it a little bit. So to encapsulate complexity. And by encapsulating complexity, we carry around data and characteristics and capabilities. State, which would be data and attributes, behavior, are bundled together. And this scales well into larger applications. By taking small units of encapsulation, we can make larger, greater things without having to think about all of the small details. Objects and classes facilitate code reuse. When we inherit, when Sandy inherits the characteristics of dogs and dogs inherit the characteristics of mammals, we don't have to create mammals and animals every time we create a dog. And also we have less pollution of our heads, less cognitive load than bare functions and data structures would be. In the C world, before we really were thinking in terms of objects, you'd have all this data and all these methods and functions and subroutines that could be called on our data, and it was always a big mess trying to keep track of everything unless you were clever and started passing around handles to represent objects or pointers to represent objects. So we want to have less pollution, less cognitive load. So let's look now at Perl's raw object system. And I have to warn you because Perl's raw object system is minimal, it's highly flexible, it's led to many modern layers, which we like to use nowadays instead of Perl's traditional object system. And so brace yourselves for the next slide, unless you're already with me 100% of the way, which everybody in here probably is. But here is Perl's object system. In Perl's object system, you have to create a constructor, and new is not any special in any way other than just by convention. In a class like DBI, we would use connect instead of new. And then we essentially bless a class, which is just a name, or bless a hash ref into a class, right? And then we have methods that we can call on it, and so we can say integer new with a value of 128, and we can print that value. So that's Perl's object system in a nutshell. Now let's look at it using Moose. With Moose, we don't have to worry about creating a constructor. That comes to us for free. Moose is available on CPAN, and there are other versions similar to Moose like Moo, which I happen to also like and use. And with Moose, we're going to say has value. We're going to, for our package integer, has value. Our value is read-only. When we instantiate our integer right here, we're going to say integer new, pass a value of 128, and if we want to get that value back, we can ask for it, and it'll print 128 for us there. So to the end user, there's no difference between a Moo class and a typical, I was at Open West, and I had my laser pointer. I was using it for the first time. Anytime somebody would raise their hand, I would blind them with the laser, so I have to remind myself not to do that. Yes? That is enforced in as much as if I were to pass a value in parentheses to my value method there, right over here, we would have an error. It wouldn't do it. It wouldn't change the value. So yeah, for Moose that is enforced. Yeah. Any other questions? I promise not to blind anybody if I remember not to. Okay. So. The benefit to Moose really is that the people who use the Moose-based solution get to go home at 5:30, and those of us that are unfortunate enough to be writing legacy-style Perl objects are going home at 9:30 at night instead because it's more work to do all that. So you can see we get essentially all of this and a lot more when we just do this little bit using Moose. So our examples today are for the most part going to be in Moose. We can create behaviors as well. So not everything has to be an attribute. You can also have behaviors, and our behavior here is going to be speak. And so we have an attribute, vocalization. Vocalization is going to contain a string, and our string will just be hello world. And our behavior is going to be speaking, and speaking is just going to be printing our vocalization. Very simple. So animals, they can speak by some definitions of speak, and they have dietary preferences, and they have blood type, whether it's warm or cold, and that sort of thing. And so an animal-based class might look like this. Package animal, use Moose, has a diet, which could be carnivorous or omnivorous. Has a blood type, which could be mammal or reptilian, cold or warm, something like that. Has vocalization, has a date of birth, by some definitions of birth, I guess, right? Has a name, and then we'll say it has a behavior, which can speak, and the behavior is to say its vocalization, whatever that might be. And an animal might be able to, in some way, present happily. However, a simple basic animal has no concept of what presenting happily might be. And so we're going to say that if somebody tries to instantiate an animal base class and they call present happily, we're going to just go ahead and die because nobody's told us how a general animal presents happily. Not all animals wag their tail or smile. I don't know how sea anemones present happily, for example. So let's move on from this for a little bit. So a dog is a warm-blooded type of animal that vocalizes with a bark and is omnivorous and presents happily by wagging its tail. And so let's go ahead and create that. We're going to say that our dog has a blood type of warm, and now we are overriding the blood type right here by providing our own blood type as we extend the animal base class. We also are going to override our diet and override our vocalization, and we're going to provide a wag-tail method. And the wag-tail method is going to be called by our presents happily. So now we have a way of presenting happily, and we have a generalized way of presenting happily that hopefully all animals can define their own version of presenting happily. So we're using inheritance, and we are overriding our base class with a present happily that calls out to our own internal version of happy moments. So if we're going to wield a happy Sandy object, we're going to instantiate our dog, Sandy, date of birth 2003. This is why I said Sandy. That's why I've occasionally used her name in past tense. She wags her tail, she speaks, she barks. Bark is the same as speaking, except that we like to use speak because we can apply speak across all types of animals, whereas bark would be specific only to dogs. We'll get to that again in a minute. She has a name, and she can present happily by wagging her tail. So we're not going to really call wag tail too much. We're going to say present happily because that's a more generalized approach to discussing how animals behave. We can request her name. We can say that she eats like an omnivore, like a carnivore, and that she vocalizes by saying bow wow or whatever it is that we said that she does, and that she is a ref pet, which would be a dog. So we can simplify inheritance a little bit. We can say package foo use moose has value, and the value is read only, and we can say foo printable, which extends foo, and printable has a word and it has an output, and the output can output our word and it can output our value. And so here we're extending the foo base class by adding some behavior. And this is one of the fundamental concepts of inheritance, is that we are able to extend our base classes and provide additional functionality and provide additional state. Let's talk for a moment about roles, because once we start going down the path of extending by providing additional features, we might want to be talking about roles. In inheritance, we say that inheritance represents an is-a relationship. And in an is-a relationship, it's really easy to say that a dog is an animal, and that if all animals can present happily, dogs present happily by wagging their tails, but we can call the present happily method. If we're going to add additional behavior, we want to usually use a does relationship. Dogs do go out in the yard and dig holes in the lawn, for example. And so we might have a role go out in the yard and dig holes in the lawn, all right? So let's look at an animal role. We're going to say use moose role, and we're going to say that this requires diet and requires blood and requires vocalization. So our animal role requires that these attributes be implemented by the thing that implements the role, by the thing that uses the role or consumes the role. We're going to say that it has a date of birth and it has a name and that it has the behavior of speaking, of vocalization. And so to use the animal role, we're going to create a package dog, and the package dog is going to implement our blood type, which was required. It's going to implement our diet, which was required right here, So I guess it wasn't, and it's going to implement our vocalization, and it's going to implement some of the behaviors that are specific to a dog. And it's going to do that with the animal base class, or with the animal role, sorry. So my dog Sandy with an animal role, we're going to instantiate Sandy, and she works pretty much exactly the same way as through inheritance. But conceptually, to somebody who's extending and working with the animal, it's much easier in many cases when you're adding behavior to look at roles. So roles versus inheritance. Not everything we model fits in a simple pattern of this is a that. Many things fit the this does that, or this has that attribute, as opposed to this inherits from. So if you look at me, for example, I inherit from humans, but I also inherit from programmers, and I also inherit from my father and my mother, and that gets to be kind of complicated and kind of complex. But if you look in terms of roles instead, I do human behavior sometimes, I do programming, I do fatherhood, and that's conceptually simpler to reason about often. And so we many times prefer using roles when the roles are not trivial, or when there are more than one role that needs to be composed into something, rather than using multiple inheritance. So let's go back to our Dremel tool again, because this is kind of a fun example for me. The Dremel tool does only one thing, and the one thing it does very well. It just spins a bit, and it spins that bit super fast, anywhere from, 3,500 RPMs up to 35,000 RPMs, depending on what you set it to, right there with its mutator. But it accepts a whole bunch of bits, and so here's where we get to talk about polymorphism. In polymorphism, two objects of different classes can be treated as though they're the same type of object if they provide a common interface. And so, in this little picture here, what is my polymorphic thing? The drill, actually the bits are the polymorphic thing, because all of them have the same user interface, right? They all have the same little thing that plugs into my generalized tool of the Dremel tool. So, two objects that inherit from a common ancestor typically share the features of that common ancestor. So duck typing is a form of polymorphism, and we use duck typing a lot in Perl. If it can quack like a duck, it's sufficiently duck-like to be considered and treated as a duck. So we're going to go back to animals again, because I promised never to talk about animals in my talk. That's all I've been doing. We're going to say a cat uses moose, which is kind of ironic, but anyway, has blood type, and it has a diet, it has a vocalization, and its vocalization is represented by purring. And so with animal, we're going to consume the animal's role. Now we're going to look, dogs and cats both have animal traits. And so let's treat dogs and cats as polymorphisms of the same animal base. And so I can say dog new, name Sandy, and date of birth 2003, and I can say cat new, name Mojo, and date of birth unknown, because that was my neighbor's cat back in 2003. And so neighborhood pets, we have a dog, and we have a neighborhood, and we have a neighbor cat. And so now for each neighborhood pet, we're going to print the name, Sandy and Mojo, and we're going to ask the pet to speak. And the dog will bark and the cat will meow. We're treating both pets the exact same way. We're treating both just by calling, what's your name? What are you? I'm a dog, or I'm a cat, and go ahead and speak to me. And because we've used polymorphism, we've been able to just abstract away the differences between these two animals, and deal only with those common sets of features that we want to deal with, that are simple, that they share in common. Any questions? Thoughts? Yes?
So how do you get the pet to purr?
So here in my cat class, I would say that I would create a method, an attribute purr, and then I would override speak to make speak be call purr.
You already had purr on the previous slide.
Yeah, I probably left something out. Let's see. So yeah, I should be overriding. Yeah, you're right about that. Thank you. I should be overriding speak here as well. So thank you. Does that make sense?
I mean, basically, a cat has two vocalizations. So when you say pet speak, and if the pet is a cat,
Right, so my pet class should be defining speak to use the vocalization that we want it to be using. Does that make sense? Yeah. Yeah. Per probably ought to be speak, right? Anyway. So thanks, yeah. So they both have animal traits. We're treating them both exactly as the same thing. They're both just pets, and we can assume that pets have names and that pets have their manner of vocalization or of speaking. So polymorphism through inheritance, our package animal defines a subspeak as a base in its base class, but it's going to die if we were to call speak because animals in general don't have a general version of speaking. But then in our dog class, we're going to define a speak, and in our cat class, we're going to define a meow. We can treat them both as the same once we've instantiated them. So in use, again, here's another way we can use them. We've got a dog. We're going to name a dog, and a cat, and we're going to instantiate our dog and cat into animal, and then we're going to speak for each animal. So using polymorphism, we're able to treat many objects as essentially equivalently duck-like enough to use them the same way. And this turns out to be very useful. In our business, we have lots of different types of servers. It's nice to just be able to ask the server, what's your IP address, for example, and not have to worry about whether my server is a CentOS server or whether it's some other server. We deal with that at a different layer of abstraction. So in the Dremel tool, we're going to do this. We're going to instantiate our Dremel tool, and we're going to pass into it a bit field. And this is not a bit field in the computer version. This is what type of bit. And our bit is going to be a Dremel bit of subclass cutting, and the cutting bit has a diameter of 1 centimeter. Reasonable enough? And we're going to set our Dremel tool to a rotation speed of 8,000. Here's another Dremel tool. We're going to new up another Dremel tool. This one has a Dremel bit of subtype drilling, and this one has a centimeter, a diameter of 0.05 and a depth of 0.3, and a rotation of speed of 4,500. When we go to use these, we both use them the same way. We hold the tool in our left or right hand, depending on which version of abstraction, which version of human we are, and we're going to spin it at the speed that it was started up at there, 4,500 or 8,000, and we're going to use the tool. They both work the same way, and it's the same exact tool, but it's being passed in different subclasses of the bit. So the bit is the polymorphic piece here. So here's our Dremel class, which is read-writable because we can change bits, and it is a Dremel. We're going to make sure that it's getting passed in a Dremel bit of some sort. We're going to ask that the thing that's being passed in to our bit is a Dremel bit, and we're going to be able to set the rotation speed. And so a Dremel tool accepts a bit. Bit types inherit from Dremel bit. Subclasses include cutting, polishing, grinding, and drilling. Bit attributes could include thickness, depth, roughness, etc. But the single Dremel tool doesn't care what tip it's been given, so long as the tip has the expected attributes and behaviors. The attributes being it has the piece that can be inserted correctly, right? And it can spin. So polymorphism is the provision of a single interface to entities of different types. A polymorphic type is one whose operations can be also applied to objects of some other type. Just another example, we have an array. We're going to create an array that contains A, B, and C. Or we're going to create a linked list that contains A, B, or C. Both of those can implement a pushback. Both the array and the list can implement a pushback. In other words, you can add something to the end of a linked list, and you can add something to the end of a Perl array, for example, or a C++ vector. Both of them can implement an at. The implementation of at for an array is much more efficient than the implementation of at for a list, because a list needs to start at the beginning and work its way through. But we can essentially treat them both the same way. They're polymorphic types, essentially. And we see this a lot in C++ with the container classes. So polymorphism is a means toward generalization. And the Dremel tool was my example of a generalized tool. Encapsulation is a bundling of behavior and state. And abstraction is the elimination of complexity for the consumer, for me, for the people using our classes, by encapsulating detail and exposing an interface that should wipe away cognitive load. This can get us into trouble, and we'll talk about that in a moment here too. Inheritance is to specialize a more general type by encapsulating more specific attributes and behaviors, and to factor out common behaviors and attributes into parents that children may inherit from. And polymorphism is leveraging a common interface or common portions of an interface so that surrounding code doesn't have to care about what specific types are being implemented. In my world, if I ever have to say if server type equals CentOS, for example, or if server type equals shared, then I have code smell, because that should be encapsulated into my server classes or my server subclasses, for example. So we mentioned this quote earlier: all problems in computer science can be solved by another level of indirection or abstraction, but there's a follow-up to that, which is that except for the problem of too many layers of indirection or abstraction. Has anybody ever here used Microsoft Foundation classes? MFC? Yes, a few people have. Too many layers of indirection and abstraction. You have no idea where you're inheriting this little portion of your widget from, where that attribute came from. So if you're ever looking in documentation for what you need to, for how you need to wield this little part, this little attribute that you, or this little thing that you've inherited, you might find yourself looking back 6 layers and having to branch out through different layers of multiple inheritance as well. And so you can really get yourself into trouble with too many layers of indirection and abstraction. And I'll get to that again in just a moment. Deep inheritance with layered on attributes and layered on behaviors requires the consumer to know too much about our class. And we see this, unfortunately, I think anybody with a legacy code base sees this throughout their code base, where one little thing gets layered on here and one little thing gets layered on there, and pretty soon you have this big just ball of mud that is a God object that carries around all kinds of state and all kinds of attributes, and this one might be a little bit different from that one in some ways, and suddenly we have if server type equals this and if that equals that, and you get code smell, and you get complexity, and it becomes very hard to manipulate that type of a code base. So God objects carry around vast amounts of state, vast numbers of features. They don't do just one thing and one thing well. They do lots of things. They inherit from many parent classes. They have many complex and possibly changing attributes. And this, to me, was kind of epitomized in the Microsoft Foundation classes. And let's not use the word Microsoft. Let's just say foundation classes of a legacy code base, right? Because our code base and many other code bases are guilty of the same types of things. So we should strive to limit layered in state and favor composing in roles rather than inheriting from many layers of multiple parents. And we should be wary of inheritance of thick classes with lots of state and lots of behavior just when we need to obtain small aspects of state and behavior. We should do our best at any point in time as we're dealing with complicated classes to try to simplify the interface that our consumers of our classes are using. Because any situation where you're having to say if the type is this, or where you have to dig through multiple layers in documentation to find where an attribute comes from, that's code smell, and that's inelegant creation of abstractions. You know, a Perl hash is such an elegant abstraction, but there are so many inelegant abstractions that we see in our daily work lives. So we should strive to keep our classes simple and to keep our attributes minimal, to keep our state changes minimal, make our objects as immutable as possible, keep your behaviors predictable, keep our layers simple, and carefully plan our abstractions. Easily said, hard to do, right? Thank you. There are design patterns and guidelines that we can do research on, and I encourage people, at the end of the talk, I'll provide some resources for further discussion and learning. But we should always be considering the notion of single purpose and single responsibility when we create classes and instantiate objects of those classes. And we should always opt for classes being open to extension but closed for modification. So easy to subclass or easy to compose with, but closed to actually modifying by adding additional attributes. Or you end up getting just these big, I need to add a feature, and so you start adding a feature in just the most the easiest place to get it done in turning your sprint, but maybe not the easiest place to maintain 6 months down the road or 6 years down the road. So the resources that I wanted to point out, you can actually learn a lot from Perl Obj, which is in the Perl documentation. Intermediate Perl, I really like this book. I first got that book back when it was called Perl Objects, References, and something else. Yeah, the first version. And it's changed a little as it's gone into more recent versions. Intermediate Perl is a great book. Modern Perl from Chromatic is also fantastic for going through the dog and cat discussions, but also looking at the Moose way of doing things, the Moo way of doing things. Look up Solid on Wikipedia and then read some of the references that leads to you. Single purpose, open to subclassing, essentially, Lifscoff substitution, and so on. Anyway, that's a great resource to look at and do some study on. And then also, eventually you're going to want to look at this book, Design Patterns, Elements of Reusable Object-Oriented Software. That's a book that really discusses in depth object design patterns. Now, Perl provides a lot of the design patterns to us for free, but it's really worthwhile to get to know what the design patterns are and to learn what they are so that we can recognize them as we're using them, recognize code that uses them, and start creating code that leverages them to our advantage in creating nice abstractions and nice encapsulations. So anyway, that's everything I have prepared for today. Are there any questions? Yes?
I noticed on your new operator you're using the arrow.
Yeah.
I would think you'd use : because at that point you don't have an instance of the class.
So a class is just a string, essentially. And the string could have been, for example, class : foo : bar, but you still would use the arrow operator when you call your constructor, because the arrow operator makes it so that the thing on the left-hand side, that string, gets passed in as the first argument to your constructor. The first argument would be, is expected by convention to be the class name. And so when you instantiate your object and internally a bless is called, the bless would be past that class so that you're blessing your object's attribute storage.
You lose the class.
Yeah, that's right. You lose the class name and the ability for inheritance to work easily. Yeah. So good question. Yes?
In your animal example,
Yeah.
you basically had a sub in there that died, and that was the protection against instantiating at too high of a type level.
Yeah, that's...
Still really generic.
Yeah, in C++ you would call that a virtual class. In other languages it would be an abstract-based class. But that's the idea.
But like in C++ and in other languages, you're barred from actually instantiating the class. It puts the error really close to where someone made a mistake of typing the wrong digit.
Right, and so in Perl you could achieve that if you're using the historical old version of writing your own constructors. You could let your constructor die. In a Moose world, I suppose you could make build args die or build die, which are methods that are called around the constructor. Yes?
You can also use roles for that.
Yeah, that's right. Yeah, roles a role to enforce that this is a pure virtual or a abstract-based class. Yeah, thank you. Does that answer your question?
Well, I haven't seen how you could define a role without providing the sub, some implementation of the sub. Is there anything close to like a true virtual where you don't have the sub implemented, but it's somehow required?
So in roles, you can say requires, but not actually implement the thing that you're requiring, and then you will have a death if it's not implemented in the subclass or in the class that composes in the role.
Okay.
Does that answer it? Yeah.
It's close. I'll have to do some.
Yeah, look at that. Look at the requires in, for example, Moose role or Moo role, either one of those. Yeah. Thanks. Any other questions? All right, thanks for coming today. You're right, this microphone started out way up by my lips and traveled down to my laptop screen.